Right, hello, this is part 2 of the chemistry for paper 2. First part was looking at rates of reaction. This time we're going to look at the story of crude oil and how crude oil goes all the way from actually being made, dug up, separated and then actually used eventually to make plastics. So we're going to start off by looking at where crude oil comes from. So originally then, fossilised remains of plankton make crude oil, and it's buried deep underground because where the remains have died and sunk to the bottom of the sea floor, and then more layers of sediment and more layers of sediment and more layers of sediment on top, it ends up being squashed and squashed and squashed and going further down into the porous rocks in the Earth's crust. And then eventually it just sits there and something happens, and scientists are not sure what it is, where over millions of years that plankton actually condenses down into this thick black soup, which is crude oil, which is made of hydrocarbons. And we're going to have a look at that in a moment. We say that it's a finite resource, it's non-renewable. And like I say, it's made of hydrocarbons. If you're asked the question, what chemicals are in hydrocarbons, then you must use the word only. Only hydrogens and carbons. Usually that's a 2-mark question because they want you to say it's only those chemicals in there in the first place. So the crude oil, deep underground. So it's found, there's lots of technology nowadays that can help to find it, and we drill down and we get the crude oil out. Then it's transported across to different countries to their refineries. Now, you may be asked some questions about the environmental impact of this, and obviously if you've got tankers that split as they are being transported across the sea, then you could have environmental issues with oil slicks on the top of the sea and wildlife being affected. Or you could even be asked about political problems. So, for instance, a lot of crude oil comes from countries that we could potentially end up being at war with. So you have to make sure that relationships are kept peaceful so that you can get the crude oil. Because essentially we don't have hardly any of it in this country. We have to depend on getting it from other countries. So I've got my crude oil. I've delivered it now to the refinery, and I now carry out fractional distillation. Now, usually these sorts of questions are quite big questions because they ask you about the process of fractional distillation. So, crude oil is put into this fractional distillator and it is heated up. And when it's heated, it evaporates. And in that crude oil, you've got short chains, medium chains and long chains. And the short chains, because they're less dense and usually gases, will go to the top of a fractional distillator and then are collected at the top. The medium chains, which are more like your liquids, will come out in the middle, and then your longer chains at the bottom. Now you need to make sure you know the order. So it's refinery gas at the top, petrol, paraffin, diesel, fuel oil, and then bitumen, which is like the residue that's left over, and they use that to make the tarmac that they put on the roads. Now if you look at the properties here, you'll see at the top they are less viscous. They've got low boiling points, they are more volatile, easy to ignite. So these ones at the top here, very low boiling points, so these set on fire much quickly. Whereas at the bottom, it's the exact opposite. High boiling points because the chains are longer, less volatile, less easy to ignite. Okay, so if I look at some of these fractions that have come out of here. This is where we'll start to look at the alkanes and alkenes. So generally, what comes out of the fractional distillator are alkanes. And I just want to talk about the difference between an alkane and an alkene. And the alkenes will make more sense in a minute when I look at cracking. So alkanes, if you see this diagram here, you can see this is a picture of an alkane. It's got carbons in the centre. It's got single bonds onto the hydrogens, and can you see that they're all at 90 degrees? And I always say with an alkane, every 90 degree needs to be filled up with a hydrogen, and then we say that that's saturated, okay, and that's an alkane. Now, the four basic alkanes you need to know are, and if you see, look, they all end in ane: methane, CH4, ethane, C2H6, propane, C3H8, butane, C4H10. Now, if you need to know how to work out the formula, because it might be that the exam board tells you how many carbons there are, but then asks you to work out how many hydrogens. Now, there's two ways you can do this. You can either learn this formula, which is Cn, n just means any number, H, two lots of carbon, the number of carbons that you've got plus 2 on the end. Now, the other way you can do it is if you think about how many carbons you've got and every 90 degrees is full. So if you just double up your carbons and then add 2, because that's basically saturated at every 90 degrees. So alkanes are saturated. Alkenes, on the other hand, are what we call unsaturated because they are not completely full. They have a double bond. I always think of alkene has got 2 E's, alkene, double E, double bond. They're unsaturated, and if you want to know the formula for an alkene, you just double up the number of carbons that you've got. If I want to test an alkene, I use bromine and it turns from orange to colourless. You must say colourless because it's not clear, because you can have something that's got a colour but you can still see through it. So you have to say it becomes colourless. Now, if I now look at burning fuels, because now I'm looking at taking some of those alkanes and I'm talking about how I can burn them to get the energy from them. So you've got two types of combustion, which is a posh name for burning. So you've got complete combustion and incomplete combustion. If you're talking about complete combustion, it's all the fuel is burnt with enough oxygen, and your products that you make are carbon dioxide and water. I always look at this and think, if I change the word fuel there and put the word glucose, that is exactly the same equation as for respiration. So essentially, we are carrying out this equation in our bodies, but obviously we don't set it on fire. So if I look at this equation here as an example, if I took the fuel of methane and I joined it with oxygen, I would end up with carbon dioxide and water. You may be asked to actually balance that equation. Remember the rules, and this was in chemistry part 1, paper 1. To balance an equation, you can only ever put a big number in front of the molecule. And if you remember, it's because I said to you, if you've got H2O, that's water. If I stick a little number 2 on the end, H2O2, that's hydrogen peroxide, and that's highly dangerous. So, what do I do first of all? I write down a list of my chemicals, my reactants going in. I write down exactly the same list of reactants coming out, and I write down how many there are to start with. So originally I had 1 carbon, 4 hydrogens, 2 oxygens. On this side I had 1 carbon, 2 hydrogens and 3 oxygens. So my problem there to start with was hydrogen. I'd got 4 going in but only 2 coming out. So if I put a big number 2 in front of water, I've now got 4 hydrogens and I've now got 4 oxygens because I've got 2 on the water and 2 on the carbon dioxide. Now my other problem is on this side I didn't have enough oxygens, I'd only got 2, so if I double up the number of oxygens, so it's 2 O2, that is now a balanced equation. If though we're talking about incomplete combustion, this is when not all of the fuel is burnt. And the problem you've got then is you make carbon monoxide and soot. And soot is, if you put a beaker onto a Bunsen burner and you just leave it on the orange flame, you will notice on the bottom of the beaker it just looks like black powder. Well, that's the soot, because the orange flame is incomplete combustion. You are not burning all of the fuel, and that soot is evidence of it. But the biggest problem you've got is the carbon monoxide. And we call that the silent killer, because if you produce enough carbon monoxide and it goes and you breathe it in, you can't taste it or smell it because it's odourless and colourless. However, what it does is it goes into your body and attaches to your red blood cells, and it stops your oxygen from attaching, and so you end up suffocating and dying. Now, just a little life lesson here, not just for your exams. But if you ever have any family members who are starting to get tired all the time and having lots of headaches, it might be worth seeing if any of your gas appliances need servicing because they're not burning all of the fuel. The other part I'm just going to mention, I'm just going to sort of throw this in here while we're talking about pollution, is nitrogen oxides and sulfur dioxide, which can also cause pollution and can cause acid rain. Okay, so back to our story then. So I'm taking my alkanes that I talked about up here, which had come from the fractional distillation over here. I'm taking my alkanes and I'm now going to carry out this process of cracking. Now, why do I need to carry out this process of cracking? If you look at this little table I've just put on here, I've just listed the alkanes and I've just put a little table to say, okay, I've made 100 units of each of these. However, for the fuel oil, I only need 50, but for petrol, I need 150 because there's a lot of cars out there that need petrol and we don't make enough. So what I can do is I can take this longer chain fuel oil and I can carry out this process of cracking, and I can crack it into a shorter alkane and I'm left then with an alkene. So the fuel oil made 100 but we only need 50, petrol made 100 but we need 150. Take the long chain fuel oil and carry out cracking. The two conditions you need are a high temperature and a catalyst, and that's usually worth 2 marks, so make sure you know cracking, catalyst, high temperature. Now if you look at this diagram, this shows you exactly what happens. I'll start off, and this is just an example, I'll start off with this alkane. I know it's an alkane because it's full at every 90 degrees, it's single bonds, and it's C4H10. I carry out cracking and I end up with an alkane of C2H6. But if you take that away from what I've got originally, I'm only left with C2H4. That doesn't make another alkane, but what it does make is it makes an alkene. And you can see I've put a double bond in there, and then the hydrogens look like they're off at a slight angle. Okay, so I've got an alkene. However, and this is the bit I think that's quite clever, although now with the environment it's bad as well. If I take that alkene, I can now carry out something called polymerisation. So if I go over to here, I can take this alkene, and this is ethene. You can see here that I've got my double bond, it's an alkene, and I can carry out this process of polymerisation where I can take that alkene, this ethene, I can then make it into what we call a monomer. A monomer, mono means one. By breaking the double bond, the hydrogens line up, and then I've got the bonds at the side. I put it into a bracket with a little n, because that means I've got one block of that monomer. If I join that monomer together, there's 1, there's 2, there's 3. I've now got a polymer, which means more than one, and because this is ethene, I've now got polyethene, which is polythene, which we use for plastic bags. So, from crude oil, I've got my petrol that I needed to fill my quota to make sure I've got enough, but I've also got that ethene that I then use to make plastic bags. And the problem we've got there is, obviously, with everything we're talking about and the issues with the environment and plastics not being able to break down, that's a serious issue. Now, the other thing I just want to mention while I'm here is this recycling life cycle assessment. Now, this is carried out to look at products and look at their life cycle. So we look at extracting the raw material, which is what we've talked about, the design and the production of that material, what's the packaging and distribution factors, the use and the maintenance of it, the reuse and recycling and disposal, and then lastly, how do we dispose of it? And obviously a lot of plastics nowadays just end up going into landfill sites and don't actually break down. And you're seeing this more and more on the news. So that's the story of crude oil, okay, all the way from being dug up from deep underground, going through the process of fractional distillation, you're carrying out cracking to get what you need, and then polymerisation to make the plastics. So that's part 2. I look forward to seeing you in parts 3 and 4.